elements in the title, like decision-making, threat, and ecological. So it seems like it's not something that should be studied by like one single lab. And to be honest, our lab actually focuses on threat. So basically what we traditionally do fear in humans. What we do is basically torture people with electrical shocks and force people to watch horror movies inside a dark room. So that's what we do before. But now, after feeling bad about that, what we're trying to do is to really try to do things in like a combinatorial way of thinking. So basically the central question of our lab still stays the same. So we are trying to ask a psychological or a cognitive neuroscience question where we ask, okay, what is fear? And what is the behavioral and neural mechanism behind fear? And that's the thing. But beyond that, we are trying to use some paradigms that's more ecologically valid than traditional paradigms where you just passively view, like feel for faces or passively receive shocks. So we think this is going to be more interesting, especially there's a lot of ecological papers sitting there where we can actually borrow to use on humans. And finally, methodological-wise, we try to use both fMRI and also some sort of computational modeling instead of including reinforcement learning model and Bayesian model. So try to capture the underlying mechanism behind the behaviors. And I'll start from the psychological topic of fear. So it's actually a quite complex topic, although it's a very primal and important emotion. There are different theorists proposing different ideas. As you can see here, there's even a paper. Basically, they ask my advisor to basically do like a discussion with all of the theorists and discuss what's the possible ways to study fear. And I'm not going to go into every detail of this. I invite you to read their works. It's all very interesting. But the thing I want to say here is that I don't think there's an absolute correct model for fear, because it's not like something in mathematics you can prove or disprove something. It's more of different theories providing you different perspectives on understand different aspects of the emotion of fear. And for us, we also try to do something that's unique and add something new to the framework. And here we're trying to adopt something we call a dimensional approach. So this originates from the work from Darwin. So my advisor is a big fan of him. And because of that, I have read a lot of Asian papers on like the red-colored papers. It's very good read because you'll find that although ancient, his view on fear actually echoes a lot with contemporary theories. So basically, we think fear and anxiety, although very similar and often taken together, can be kind of partially separated based on some characteristics. For example, if you're talking about fear, it's more like imminent and tangible threat. And if you're talking about anxiety, it's more abstract, and the threat might be more distant and remote. So a simple example would be, say I'm preparing this talk, I procrastinated till last night, and then I think, oh crap, I won't be able to finish this. So because I still have time, because it's last night, and the threat which is standing here now is also distant, so I would call it anxiety. And if I forgot I need to do a talk today, and when I'm sitting here, it's like, okay, Songqi, you need to go on. And it's like, I can't do anything, so it's threat, it's fear. So I'm trying to separate this in terms of a framework like this. And how we do that? So basically, I found this book. Basically, it's talking about the relationship between prey and predators. So you can imagine sometimes the predator is like far away, sometimes it's very close. And so that can kind of simulate this dynamics. And yeah, it's very interesting. Even if you don't do this work, I recommend to read it. And for me, I graduated last year, and I think without this book, I won't be able to graduate. And so this is a framework we are pulling out from the book. It's by Michael Fancillo and his co-workers. So I invite you to start from the right side to the left side. So imagine the natural environment. So there's a bird resting here. So here we call it a safe state. There's no threat present. And if he goes down to the ground, try to find something to eat, now he's actually in a threat environment, although the predator is not present, but there's a potential threat here. And furthermore, also they call it prey counter threat. And here you can, there's actually an orange cat lying down not far away, but luckily it's now sleeping. So we call it post encounter, where the threat is present, but not actually pursuing the prey. And finally, when it's awake and trying to hunt the bird, it's circa strike, where the attack actually happens. So along the axis, if you summarize it, the intensity of the situation is actually increasing. And if we put it in a human scenario, we'd say, okay, maybe in the right-hand side, it's kind of anxiety, and in the left-hand side, it's kind of fear. We're not promoting like a strictly dichotomous separation of fear and anxiety. I believe it's a continuum. So I think that continuum maps into a framework like this. So there's a work done on this like about 10 years ago. So you know why there's a tarantula here very soon. So basically, my advisor puts participant in the scanner. I think this is back in the UK. And then there's like a box in by the feet. And then we use an actual tarantula, and then we tell them, okay, we're going to put the tarantula inside the boxes. You see there's like different distances. And then in the scanner, they have a screen where they can actually see a live footage of the tarantula being moved. Yeah, this is before I came to the lab, so I don't feel bad about it. It's my advisor. And what they find is that before, so basically when the spider comes closer to the foot, regions including like the midbrain pH area, which is for like panic attack, very primal fear subcortical regions, gets activated. And on the other hand, when the spider is kind of distant, you're activating more cortical regions, including the VMPFC. So I think that's a very good first empirical study solidating the hypothesis we had before in the framework. But still, it's kind of passive. So the person is lying down in the scanner and he cannot do anything. He's basically perceiving the threat but not really making decisions. So what I really wanted to incorporate is a decision-making component where the person can actually use strategies to cope with the threat. So we are borrowing from another very old paper from Inberg and Deal. So it's talking about the economics of fleeing from predators. So we are introducing a concept called flight initiation distance in this framework. So basically, if you imagine, I think many of you have probably seen the footages on YouTube or something like this. So basically, like a group of zebra is kind of chilling there, and one of them might be trying to drink water or eat something, and there's like a lion or other predators trying to catch this one. So this is a typical scenario where the individual is actually away from a safety refuge, say like a herd, and then there's a threat trying to catch him. So if you look at it, there's two parameters here. So this parameter, I'll talk later. But now we're focusing on this. So basically, it's a distance between the prey and the predator when the attack happens. So what's important to that? So it's not really ideal to run away right away if you see the predator, because you are maybe drinking water and eat food, and it's economically costly for you to just go away. So actually, there's two cost functions. If you think about it, as the predator approaches, the longer you stay there, the more food you're going to get. So that's one cost function. On the other hand, the longer you stay there, there's a larger chance for you to get caught by the predator. So the danger level is rising. There's another cost function. So theoretically, there should be an optimal point where he should make the flight decision. And we believe there should be similar mechanisms in humans too. So I'm basically adapting the same framework, but instead of putting like spiders, we use computer games, which I think give us better behavior flexibility and also is more human. What happens is that they see a one-dimensional runway, and there's a safety exit, which is a safety refuge like a herd. And then the participants start somewhere in the runway. And during the entire trial, at any time, they can press a button. So the only thing you need to do is just to press a button. And then this thing will automatically move to the safety exit. So they just need to decide when they want to press that button. And you can see there are different colored dots representing different types of predators trying to attack them. And the differences of the colors is basically the predators will first move very slowly from the left-hand side, and then at a certain point, it will speed up, simulating a process where it actually attack here. And it's basically displays according to a Gaussian distribution. And so the different predators, they have the same speed. The speeds are totally the same. The difference is that when they attack. So they basically speed up at different locations, and based on like a standard Gaussian distribution. And what happens is that if the participants escape before the predator gets them, they get a monetary reward, like actual dollars. And if they get caught, they get a shock to their wrist. Also, the shock level is lower than in the UK because there's better IRB here. So you can see there's the same economic framework as I talked about before. The longer you stay there, the more money, potential money you can get, but if you stay for too long, you get a shock. And here again is basically re-displaying what I just said. In the actual experiment, because I don't believe it's like a dichotomous relationship. Oops, I'm sorry about that. Because I don't believe it's a dichotomous relationship. So I think there should be like a third condition where we actually use what we call mean predator. So the distribution is basically as a mean of the two types of distributions. And then looking at the behavioral data, so here is a histogram showing the decisions across every tribe, and this is average across subjects. So basically you can see clearly in the slow attacking condition, which is basically easier to do because the predator will kind of move slowly for a long time and then attack. They have a larger behavioral flexibility. Also, they choose to stay longer. And if you are looking at the predator that attacks speeds up very early, they have a very early escape trial. So that's very intuitive. That's very true to intuition. And also, if we look at the averages from every individual, you can see again the larger behavioral variability in the slow attacking condition. And looking at the brain data, so basically we are using like very simple single voxel fMRI analysis here. We are seeing the similar separation of what we call cognitive field circuit, which involves more cortical regions, and a reactive field circuit, which involves more midbrain circuits. So this is basically the contrast where we contrast the slow, more abstract attacking condition versus the control, and the fast attacking condition versus the control. So in the control condition, they play exactly the same game, but just without the threat and reward. So they play the same game, but if they win, there's no money. If they lose, there's no shock. And sadly, we don't actually find anything interesting or significant in the mid attacking condition. I don't really have a good explanation for that, but I think it's because those two conditions are too salient. So in the mid condition, they're kind of, okay, I'm just chilling there. I just form a habit and I'll make this choice all the time. So you might ask a question later, but I want to let you know that we are not really modeling a process as a learning process, because this is a very simple task. They learn very quickly, like which color corresponds to what kind of mean. So their performance quickly reaches like a big data scaling effect. So actually remove the first 10 trials to actually remove the learning process, so they can actually adapt to their habits. Here is looking further into a brain data. So we basically did these regions as a region of interest, and we went into this region of interest and we extracted brain signals, both signals from that. So you can see there's a clear separation of the signals within like PAG and MCC from the slow and fast attacking conditions. And so this is like the actual time course. And if you look at the average, in the experimental condition, there's larger both signal in the fast attacking condition compared to the slow one. And what's interesting is that if you look at the control, where they play the same game, there's actually no difference. So by this we can say, okay, this is a proof that it's not a difference due to task structure, but due to the different level of threat. So PAG and MCC is responsible and localized to like immediate threat attacks in the fast attacking condition. On the other hand, you can observe similar phenomena here in VMPFC and other regions for the slow attacking condition. So we think it's kind of good evidence or good support to our theoretical framework. And then because I'm not really from psychology, I have some background in engineering and computer science. So I wanted to do something computational. So this is a very, very simple Bayesian learner model. So if you are thinking about the process, they are basically learning the distribution of the attacking conditions, the attack distance, right? And we are trying to make it even simpler, because I don't really want to dig into mathematics. So we have them to do a practice session before the actual session. So in the practice session, the attackers have the same variance, but the means are different. So after that, we assume they already learned the variance. So assume they know the variance, but they are just trying to estimate the mean of the attacking conditions. So it's a very simple mean known, variance unknown, mean unknown, variance known conjugate prior. And then we basically update the information on every trial, and it's a very simple posterior function of that. And this is showing you throughout trials how this actually converges to their final mean. So you can see that in the first few trials, there's a huge fluctuations because they really don't know what's happening. But after the few trials, they actually know like what's kind of mean position of this. And one note to this is that their perceived mean is actually all a little bit higher than the actual mean of the attacking condition, which means they tend to overestimate how dangerous the threat is. I think mostly due to they have to receive the actual shock to the wrist. And then the next step, what we're trying to do is to, based on that information, like how they perceive the attacking condition, we're trying to get them a target function, or we call utility function, to optimize. So here the utility function is basically a two parts thing. The first part is parameter beta 1, which we call their sensitivity to a shock, the parameter of their sensitivity averse to a shock. And then I caught here is the event where they get caught. And the other part is basically how they like the money. So there's another parameter here. And then MFID here is the actual money they get based on when they flee. The longer they stay there, the more money they get. And then the probability is obvious 1 minus they get caught. So it's a simple target function. And the policy, we just use the bread and butter softmax, and then we use maximum likelihood estimation to estimate beta 1, beta 2 based on all the trials. And here is what we get from the parameters. So we have two runs. We have them come in the morning to the first run, and they have rest, and then in the afternoon they do the second run. So in the morning we use the trials in the first run to estimate beta 1, beta 2, the two parameters. And here the x-axis is the pen, beta 1 parameter, which is the averse to the shock, and y-axis is how they like the money. So it's mostly normal, except for there's one person who actually kind of enjoyed the shock. I don't know why, but maybe he thinks it's very advantageous. And what I'm trying to say is the model is not absolutely perfect. I think it captures some of the process of the decisions, but because it's very oversimplified, so it's not really perfect. But what we did next is that we use a parameter estimate from the first run to try to predict the behavior in the second run. We just feed the parameters in the first run and say, okay, if that can predict things in the second run. So here the dots are the actual choices, and then the solid line. I should actually do dots, but it's too mass, so I did a solid line. It's predictions. So we did two ways to try to say how good it is. First, we calculated a simple vector correlations. You can see it's kind of messy in fast and mid condition, but I'm kind of content with what this does in the closed predator condition, where they have more time to strategize. I think it's mainly because in the faster condition, they don't really have time to think. So it's probably not a Bayesian process that's happening. It's probably simple model-free reinforcement learning. And here is a faster target condition. In the slow target condition, it achieves better correlation. Maybe it's because they actually have a better idea of what they're doing. And we also had another measure, which is basically trying to calculate the total squared errors between each pairs of predictions. And it's significantly smaller than the actual dispersion in the attacking conditions. So I think that's also a sign of this model is capturing some level of their behavior. And moving forward, we also collected the data. So it's like a psychological inventory called trait anxiety inventory. So this is basically a measure of how anxious they are as a human. So what's interesting is that there's no correlation between the behavior in the fast attacking condition and trait anxiety, because we actually call it fear. It's probably shifted far away from anxiety on the continuum, so it's not really taking an effect. On the other hand, in a slow attacking condition where we believe there's a lot of anxiety component there, there's actually a positive correlation between anxiety and fit, which means when they are more anxious, they are trying to be more conservative, they are trying not to be risky. And there are also some brain data, so I'm not going to details into brain data, but because probably I'm running out of time. But basically, they are we look at the parametric modulation by the anxiety parameter. There's activations in like the NPFC and hippocampus, where it's consistent with our hypothesis that this will be more like a cortical process. So if you remember, back in the zebra example, there's two parameters in the figure. So now I'm going to talk about another parameter. So here, what we just talked about is what we call flight initiation distance. And on the other hand, on the same process, the other parameter, which is basically how close you are to your herd or your refugee, is called margin of safety. So I think that's also worth studying, because if you think about it, The FAD is basically the online decision-making process. It only happens after the predator is present. And it's really online decision-making and it's about the spatial temporal dynamics. On the other hand, the margin of safety it happens before the predator appears. It's the decision you made beforehand. So we call it a preemptive avoidance decision. And also, I think instead of where the predator speed up, it concerns more about the uncertainty aspect. So basically, before the predator appears, the prey is uncertain of where it's going to appear. So it's about a level of uncertainty. And there's also a economics here. So if you choose to forage close to your refugee, then maybe there's like less food, less resource for you to forage, but you'll be able to escape from the predator better. On the other hand, if you choose to from kind of far away from the refugee, there's probably more reward. But on the other hand, the predator is going to be closer to you, and then you are kind of closer to a danger. So that's a trade-off. And here we are using almost the same paradigm, the same computer game on the 2D dimensional, 1D dimensional runway. But what happens is that instead of choosing when to make the decision to flee, they choose where they start. And also, because in this condition, it's kind of a difficult task. Here you can see we have 3 different conditions. They all have the same mean. The difference is in their first, there's like 2 node distribution with different variance. So this variance is half of the other. And on the other hand, there's like, we add a little bit kurtosis to this base node distribution. So it becomes replicatic. So it has a more spiked center and a fatter tail. So I try to see on these conditions where it's same mean, what's different is in their level of uncertainty, how they behave. And because it's kind of more difficult, so we let them play the same colors for 10 trials. And then we ask them to do the other colors. And by the way, both in this task and in the previous task, they get the information by looking at, so we tell them at the end of the trial where the predator actually speed up. So they do have a direct visual feedback to where the attacking position is to better facilitate their learning process. Sorry, I mentioned learning. Because it's a very short process, we only look at their decisions afterwards. So I wouldn't call it really learning. It's basically a process where how they formulate their habit. So I think it's because the final choice they make is not only associated with how good they learn, but also associated with their personal choice, like their trait anxiety, like how they want to place themselves in this situation. So again, looking at the behavioral data, I first talk about confidence ratings. So basically, we ask them to rate how confident they are in the trial to escape. They are not confident in the laboratory condition where there's a fatter tails because there are constant surprises from the edges. On the other hand, their confidence ratings in the 2 node distributions is actually pretty much the same. And what's even more interesting is that if you look at this graph, sorry, this is a serial work in progress, so this might be a little messy. So this is again showing the same thing here, but in a dot plot. So they are consistently more risk averse or conservative in the laboratory condition, but their choices in the 2 node distributions are actually pretty much the same. This blue one only has half variance than the green one, but in this task structure, they are actually making the similar choices, but they're really, really afraid of the red condition. And you can see that this is actually preserved across different subjects. So in every subject, they're actually having a higher decision or larger margin of safety compared to the other 2 conditions. And again, this is basically showing the task structure. So so we have 400 trials in total, spread out in 2 days. So this is showing you the attack distribution. So here 0 is basically the mean, and you can see there's kind of more outliers in the laboratory condition compared to the other 2 conditions. Again, we look at trait anxiety data. Because this is again a very small sample size, 24 people. So I'm not going to push this into you, but their trait anxiety is correlated with the margin of safety choice only in the laboratory condition. So basically, the more anxious they are, the more afraid they are, the more risk averse they are. But this is not true in the other 2 known distributions. I'm going to cut very quickly into the fMRI data. So basically, we are doing like a multivariate kind of searchlight analysis here. And what's interesting is that we actually find 2 clusters of VMPFC. One is more kind of posterior, one is more anterior, and according to past literatures. So the anterior part is actually more responsible for like safety choices or feeling safe. On the other hand, the anterior part is again correlated with like anxiety and risk choices. And what's interesting is that when we're looking into like region of interest searches, so basically searches are constrained in the region of interest. So hippocampus can decode all three conditions very well above chance level. On the other hand, for the posterior VMPFC, it only decodes the dangerous lipolytic condition. And on the other hand, for the anterior VMPFC, it only decodes the safety condition. So maybe that's kind of proof of the framework I just mentioned. So I think that's kind of good progress, but we're still looking at the data. So there's a lot of messy connectivity analysis we try to run, but we try to find something interesting out of it. So the take-home message is first, fear and anxiety are dynamic process involving a complex set of defensive circuits. And as I just mentioned, slow and gradual attack and fast and imminent threat involves different brain regions in humans. And also anxiety has a role play in the whole process. And finally, some higher order representations like uncertainty might be represented in the frontal lobe. Again, I want to go back to the first slide, where I really appreciate the chance of the Cosyne conference here. This is the first time of me being here before I just go to psychology conferences. So I think it's a really good chance for me to kind of talk to computational people and also ecology people, where I think we can further basically promote both areas. And finally, I want to thank my advisors, my collaborators, and all my funding agencies. And I'm going to take questions from you. Thank you.
We have time for a question or two before we break.
There is one question. Yes, maybe we can start from there.
Have you considered at all the role of like other sort of like predator-prey structures? So where, in some cases, my understanding, there's like predators that will eat prey, and that's their main kind of food. And then there's also possibilities for different types of prey. And there's also possibilities for the predator and prey to also both share a food source underneath them, and then have that like interspecies competition as well. Have you considered like how any of that would like modulate this fear response?
Yeah, I think we actually consider different types of prey and predators, not to your level, but I think it's a very good, very good idea coming to me. So we might be able to look at, as you mentioned, if sometimes the predator actually collaborate with the prey instead of competing. So that might be an interesting framework. But I can let you know that actually we are doing something looking at different types of predators. So we're trying to do something where sometimes the predators have very poor vision. So they have good vision on moving subjects, but they have poor vision on like quiet subjects. So we're trying to design a task where there are basically different type of predators, again in a computer game scenario, but they have basically different levels of field of views and how sensitive they are to the stimulus. And then the participant basically need to learn, okay, which predator is like the frog. They can't really tell, and then they can choose to freeze during the process, what we call adaptive freezing, to better facilitate the chance of foraging. So yes, I think that's definitely the direction we should go.
Okay, just in the interest of time and people going to the slopes, we will cut now and we'll see you at 4:30.
Yeah, if you have other questions, maybe we can discuss after the panel discussion. Thank you so much.
See you.
Yeah.